All right, guys, today we are talking about lesson 1.1, limits and continuity. Hopefully no one is watching this video. Okay, maybe that's not true. If you are watching this video because in class we went too fast and you just need a refresher, great. I'm so glad you're here. If you're watching this video because you already missed the first day of school, shame on you. Hopefully things get better, right? So, we're going to go through this kind of quick because most of you have probably seen it in the classroom with me, and this is kind of a review. If you lived in another state, this is one of those topics that you would have learned in a previous class. But in Utah, there's not very many teachers, there's not very many schools that cover limits. They do talk about continuity a little bit, maybe not in that word, but they don't talk about limits. So this is going to be new for lots of people. Maybe you're here to get a little bit of a refresher. So, informally, what is a limit? A limit is a y value that a function approaches as x approaches some number, okay? So basically, as I go along my graph, as I'm getting close to -6, as my x's are getting close to -6, my y value is getting close to 1. That would be the limit. As x gets close to -6, y gets close to 1. If I look at another part of my graph, if I'm moving from 0 and I'm moving towards 2, as x is approaching 2, my y value is getting closer to 1. Now, we don't care what is happening at that exact number. And that's why it's worded the way that it is. I don't care what's happening. For example, the one we just talked about, as I'm approaching 2, I don't care what's happening at 2. I care what's happening as I get close to 2. So the way that you will see this limit given to you is right here. And it looks like the limit, the way we read this, the limit as x approaches some value c. So the limit as x approaches c of my function f of x is equal to L. So what we're interested in is as I am approaching an x value, what is my y value doing? Okay, as I'm approaching it, what's happening with my y value? So for example, let's go through some of these. Number one, now all of these examples right here are using our f of x function over here on the right, okay? So this first example says my limit as x approaches -4 of f of x. So I'm approaching -4, which is right here. So as I'm approaching -4, what is happening to my y value? Well, as I'm moving along my graph, as I'm approaching -4, my y value is getting close to, what is that, 1? My y value is approaching 1. So the limit as x approaches -4 of my function, f of x, is 1. Now, this one is interesting because f of -4 is actually 1. I'm approaching my value, right? And that it's nice when that happens. Number 2 says as x approaches -1, as x approaches -1, what is my function doing? F of x is doing what? So as I'm approaching -1, so I'm at -3, -2, at -1, I'm getting close to 4. My y value is approaching 4. Now, here's where we need to be careful with limits because f of -1, if I'm looking at my example right across, f of -1 is not 4. F of -1, that open circle means that f of -1 is actually down here. F of -1 is 1, but my limit is 4. I'm approaching 4. Even though my value isn't 4, it's down at 1, okay? And that's where limits and we got to be careful with the different terminology, the different math language that we're using there, right? We're approaching 4. We don't actually reach 4 because once we get there, we drop down to 1, but we're approaching 4, okay? All right, example number 3. The limit as x approaches 2 of f of x. So as I'm approaching 2, I'm going along my function, I'm getting closer and closer and closer to 2. I don't care what happens when I get there, but as I'm getting close to 2, again, I'm going to 1. Oh, where'd my pen go? I'm approaching 1. When I actually get there, if I want to know number 10, what happens when I get to 2? Well, f of 2 is a whole, and on this one, there's no other value shown for at 2. So f of 2 actually does not even exist, which is kind of cool. I can find what I'm approaching, even if once I get there, there's not a number to get to, but I'm approaching 1. All right, example 4. The limit is x is approaching 3. I like this one. As I'm approaching 3, let's get past that dumb hole at 2. As I'm approaching 3, look at what my function is doing. If I'm approaching 3 from over here, my function is getting lower and lower and lower and lower and lower. And you would say, well, that arrow means that it's going down to what? Negative infinity. And same on this side. If I'm approaching 3 from over here, I'm getting lower and lower and lower. And that vertical line, you know, that means you're never going to actually get to 3. But as I approach 3, I'm approaching, my y value is getting closer and closer to, a lot of people like to put negative infinity. I prefer it does not exist because I'm not approaching a value. I'm just constantly getting more negative, right? Either of those on the AP test, it would take negative infinity or does not exist. It's going to take both of those. Now, once I actually get to 3, the value f of 3 is equal to nothing because there is no value there. That makes it an asymptote, right? So that's my does not exist. Okay, number 5. Now things get interesting. Number 5 wants me to look at as x approaches 5. So this one's a little bit different than the others because when I was going to -4, no matter which side I was coming from, I was approaching the same thing, right? But look at number 5. As I'm interested in going to 5, or to 5 right there, right? So as I'm coming from this side, as I'm approaching 5 right here, I'm getting closer and closer to -1. So from over here, I'm getting closer to -1. But from the right side, as I'm approaching 5 from above, is how I would say that. As I'm approaching 5 from numbers bigger than 5, I'm not going to -1. I'm actually going to the number 2. I'm getting closer and closer to 2. That's a problem because going from different sides, I'm going to different numbers. So the limit does not exist. At least the limit as x approaches 5 does not exist, because it's going to 2 different numbers. At 5, f of 5, if I look at number 12, my actual value is going to be the upper number. It's going to be 2. That's what that black dot means, right? But I don't approach it from the left and the right. And this gets us into something called one-sided limits, okay? Because there's another part of this definition, and I don't know why this textbook doesn't use it earlier, but something that you just learned is that the limit can't just approach a number, it has to approach the same number coming from both sides. So the way that I write that, and this is maybe something we should add up here in our, let's add this to our notes up here at the top. What I'm going to say is the limit as x approaches some value, we'll call it c, from the left. And the way I write that is I put a little negative up here after the c. So my limit as x approaches c from the left of my function f of x, that limit has to equal the same thing as if I approach c from the right. Okay, those two have to be the same thing for the limit as x approaches c of f of x to exist. All right, if they don't both equal the same thing, then the limit does not exist, okay? So let's look at 6 and 7. We call these one-sided limits, and we already actually did this one, right? Because 6 says, as x approaches 5, and notice that little minus sign, from the left. So as I'm approaching 5 from the left, I'm approaching -1. So the limit from the left does exist. Now, if I'm approaching 5 from the right, if I look at number 7, x is approaching 5 from the right. From the right, I'm approaching 5, and I'm getting closer and closer to the value of 2. Those are not the same thing. They exist separately. The limit on the left exists, and the limit on the right exists, but I cannot say that as x approaches 5, that limit does not exist because they're not approaching the same thing. All right? Okay, let's move on to continuity, something that maybe sounds a little bit more familiar. So continuity, you've heard the word continuous a lot in some of your previous classes. Again, informally, I'm just down here at the definition of continuity. A function is continuous where it can be drawn without lifting a pencil. So if I can draw my function and never pick up I guess that's probably a bad example because I just made it not a function, right? If I can draw my function without picking up my pencil, it's continuous. But if I have to stop because there's a hole right there and keep going, it's no longer continuous. It's continuous in lots of other places, but right there, it's no longer continuous. So formally, the definition that we use, a function is continuous where its limit and function value are the same. So a function is continuous if the limit and the function value are the same thing. Or in other words, if I'm approaching a number and I actually reach the number, then that function would be considered continuous, okay? The definition, what it looks like, and what you're going to see a lot on the AP test and the homeworks and the things that we do is this definition right here. A function of f is continuous at an x value c if and only if, as x approaches c from the left, that is equal to x approaching c from the right, which is also equal to the value of f of c. So for something to be continuous, I have to look at the limit from the left and the limit from the right and see if they're the same. And I also have to see if that function actually reaches that value. So we're going to make a little note right here because you are going to be asked to prove that something is continuous. So right here, I want you to put prove continuous. In order to do that, the first thing that you need to do is see if the limit as x approaches c of f of x exists. Does the limit exist? From the left and the right, is it going to the same place? Then you need to see, does the value f of c exist? Right? Is the function defined there? Does that value exist? And the third thing that you need to see, are those numbers the same number? Okay? Does the limit exist? Does that value exist? And if so, are they the same thing? Okay? So in this class, there's another little note right here that we work on 3 different types of discontinuities: holes, vertical asymptotes, and jumps. A hole is what it sounds like. A vertical asymptote is what it sounds like. And a jump is where the graph jumps from one position to another position. Those are all different places, different types of discontinuities, all right? There's another one that the book mentions right here. It's called an oscillating discontinuity. If I look at, I think I still have it. Okay, so right here I graphed the function sine of 1 over x. And this is a really cool function. This is what it looks like. And as you notice, as I'm approaching, let's look at as we approach 0, what happens? As I approach 0 from the left, I start going down. and then I go up, down, up, down, up, down, up, down, up, down. Over and over and over again. As I approach from the right, I'm going up, down, up, down, up, down, up, down. Now, what's cool about this function is this is what's called an oscillating discontinuity. Because if you notice, my function is going up and down and up and down and up and down. The closer I get to 0, look at how close these oscillations are getting. Right here at the bottom, you can see that they're at the rate that it's going up and down is getting a lot closer together. And as I zoom in, you'll notice that these lines just keep getting closer and closer and closer together. It is still oscillating. Okay, my function is still oscillating. It's just oscillating closer and closer together. So that is called an oscillating discontinuity. Those don't really come up in the AB class. I believe that Calculus BC will get into oscillations a little bit, but we don't really see that in this class. So you only need to worry about those other three: holes, vertical asymptotes, and the jumps. So the next couple examples in your book, example 13. List, this is the same function. We've already looked at this function. And it says to list the x values of the discontinuities. So I am looking for holes, vertical asymptotes, and jumps. So as I go across my function, I'm still drawing, I'm still doing good. When I get to right here, I run into a hole, and that's at x equals 1. So I have a discontinuity at x equals 1, and that discontinuity is a hole. If I keep going, so from there I follow my graph, and all of a sudden when I get to 2, I have another discontinuity. So at x equals 2, I have another discontinuity, and that one is also a hole in the graph. So let's keep going. As I go from 2 down, as I follow that one along, I'm going to hit this vertical asymptote, and I'm just going to keep going down and down and down forever, but I'm never going to actually be able to reach 3. So that gives me another discontinuity. So at x equals 3, I have a vertical asymptote. Now, if I keep going, after 3, I'm going up. I hit 5, and this is where we have that weird discontinuity we talked about before. My graph goes to -1, but then it jumps up to, 2? So at x equals 5, I have a jump discontinuity. My graph jumps. Now, guys, these are really easy to see. I know I'm going slow, and I'm probably oversimplifying this, but it really is that simple. I guess I'm probably making it harder than it should be. Discontinuities are very easy to see visually, right? It's not hard to say, oh, look, there's a hole in the graph. Oh, look, there's an asymptote, especially because we draw asymptotes with dashed lines. Oh, look, the graph doesn't touch right there. Discontinuities are really easy to see. They're a little bit harder to find algebraically, which we'll do another time, but visually, they're pretty easy to see. Now, discontinuities have 2 different types, and this is the last thing that we're going to, maybe not. We probably need to look at piecewise functions too. Discontinuities, there's 2 different types. There's a removable discontinuity and a non-removable discontinuity, okay? Removable discontinuities are the holes. So that's a removable discontinuity. That's a removable discontinuity because that value has been removed. Asymptotes, like this one right here, that is not a value that has been removed, okay? That value does not exist. So that is a non-removable discontinuity. This jump right here, that is a non-removable discontinuity, okay? So when it says which of the discontinuities right here in example 14, which of the discontinuities from example 13 are removable? Well, removable are the holes. So x equals 1, x equals -1 is a discontinuity. Did I do that earlier too? Oh, I did. I didn't put a negative sign right there. Shame, shame. X equals -1 is a removable discontinuity, as well as when x is equal to 2. Those are both removable discontinuities. Okay, let's move on. Algebraically, at x values where a function is continuous, the limits can be found with direct substitution. And that's exactly what it sounds like. You directly substitute the number into the function. Now, we didn't have to do this earlier because where'd my function go? Earlier when we were finding limits, it didn't give us a function. It just gave us a picture. Now it's going to give us an algebraic function, and it wants us to find the limit. So on number 15, the limit as x approaches 3, here's my f of x function. What's that limit going to be? The first thing I always am going to try to do is take that x approaching 3, and I'm going to try to plug it right into the function. 3 times 3 squared plus 2. Now, if I actually move on with the math, 3 times 3 squared, that's 3 times 9 plus 2, that's 27 plus 2. Why am I doing this? You guys are in calculus. The answer is 29. The limit of this function as x approaches 3 is 29. There are parts of the test, and maybe I'll save this for something that we can talk about in class. In fact, you know what? I am. It's going to come up 100 times as we are having class discussion, so we're not going to worry about it right here in the video. So number 16, the limit as x approaches 1 of this function. Okay, well, let's try plugging in x equaling 1. Now, this doesn't always work because sometimes our value isn't the same, right? Sometimes bad things happen. So 1 squared is 1 plus 1, that's 2. 1 plus 1 is 2. 2 over 2 is 1. Okay, number 17, the limit of as x approaches pi thirds of cosine of 2x. Ooh, I like this one. All right, so let's try plugging it in. Whoa, sorry, got excited there. Cosine of 2 times pi thirds, which is just the cosine of 2 pi thirds. And because you worked so hard to memorize your unit circle, you know that the cosine of 2 pi thirds is the x value at 2 pi thirds, and that cosine is equal to -1/2. So the limit as x approaches pi thirds of cosine of 2x is -1/2. I can just directly plug it in and get a value. Sometimes you'll plug the numbers in and not get something. Bad things will happen, things go wrong. And that means that there's a problem, that at that point on the graph, we might not be continuous. There might be a hole, there might be a vertical asymptote, something is going wrong at that exact value. So let's look at piecewise functions, and then I'll let you actually get out and practice this a little bit. So for piecewise functions, one-sided limit evaluation is often necessary. It is almost always necessary when you're doing piecewise functions because they give you the piecewise function on purpose. Look at what they did. Here's f of x. So when x is less than or equal to 1, I'm going to use 4 minus x. When x is greater than 1, I'm going to use 4x minus x squared. Now, they gave me a piecewise function that changes functions when x at x equals 1. So guess what my limit's going to consider? What happens at that point? So when x approaches 1 of f of x. Now, remember, my limit, technically, I'm supposed to be checking the left and the right. So my limit as x approaches 1 from the left is going to use the top function because that's going to use numbers that are smaller than 1, which is that top function right there. So as I approach f of x from the left, I've got to use the 4 minus x, but I'm approaching 1, so I can go ahead and plug that in. So 4 minus 1, that's 3. Woohoo, easy math. Now let's look at what happens as x approaches 1 from the right of my function? Well, if I'm approaching from the right, I have to use the bottom function because my numbers are bigger than 1. So I have to use 4 times 1 minus 1 squared. Well, 4 times 1 is 4. 1 squared is 1. So this value becomes 3. So even though it's a piecewise function, from the left, I'm approaching 3. From the right, I'm approaching 3. And when I actually get there, my value is 3. So cool, my limit as x approaches 1 of f of x is 3. So what? On the left-hand side, we've got some function like this, and then we get to the x value of 3, and now all of a sudden I have an upside down parabola. So either way, where they meet, they both approach 3. So it's nice when it works out nicely like that, right? Okay, 19, g of x. It's asking what happens as my limit approaches 1. So as x is approaching 1, I have to consider the top function when I'm coming from numbers that are smaller than 1. So the limit as x approaches 1 from the left of g of x, so I've got to use that top function. So 3 times 1 minus 1 cubed. Well, 3 times 1 is 3. 1 cubed is 1, so 3 minus 1 is 2. Now, my limit, where did my pen go? My limit as x approaches 1 from the right of g of x, this time I've got to use my bottom function because I'm using numbers that are bigger than 1. So I've got to use 2 times x squared, so 2 times 1 squared minus 1. 1 squared is 1. 2 times 1 is 2 minus 1. That's 1. So this piecewise function, from the left, I'm approaching 2. From the right, I'm approaching 1. That is a problem because 2 and 1 are not the same number, at least not in this class. So that limit does not exist. Last example, for this same function, so it wants me to use the same function right here. What is the limit as x approaches -1? I like that the book added this question because I've seen the AP test do this. I told you before that usually if the piecewise function changes at 1, that's probably the limit that you're going to approach. That's not always the limit that you're going to approach. It's probably going to happen. But look at this one. It wants me to look at what happens as I approach -1. Well, in my function, -1 is less than 1. So I don't even have to use my bottom function for this one because whether I'm coming from the left or the right, I'm using the top function. So I'm going to just try plugging x being -1. I'm going to just plug that right into the top function. 3 times -1 minus -1 cubed. 3 times -1 is -3. -1 cubed is -1, so I'm doing minus a -1, which is like adding 1, so I get -2. So that limit does exist. The value is -2. So usually it wants you to consider where the function changes. That doesn't mean it's always going to be the case, so just be careful as you're reading the problems that you're reading what it wants you to do, especially with all these negative signs. When I have something like limit as x approaches -1, and I'm also seeing things like limit as x approaches 1 from the left, those are easy if I'm going fast and not paying attention to interchange. So just take your time, make sure that you are reading the questions carefully. Now for the homework, the rest of this, don't worry about the rest of this. The greatest integer function, that is part of the BC curriculum. That is not part of AB curriculum, so you can go ahead and scribble out the rest of the notes right there, examples 21 and 22. Homework is going to be, 1.1 homework is all of the problems, all real numbers. I want you to do 1 through, how many are there? I've got the book right here in front of me. 1 through 42. Oh, that's not too bad. So there, I want you to do 1 through 42, but I want you to skip number 22. That uses the floor function that we just crossed out. So do all of the problems except for number 22. As the year goes on, we'll kind of reevaluate homeworks. This is the first year I've used this textbook, so we'll kind of find a balance of how many of these problems is a reasonable thing to ask for you to do while you're at home. So good luck.